A custom web UI will be used to demonstrate multiple IPAM behavior. On this page, there is information collected from different Kubernetes CRDs. Cilium node, Cilium IP pool, and pods. And combined, what we have is the following. We have a cluster defined with a IPv4 pool, an IPv6 pool, cluster-wide default pool. And from this, we have 4-node cluster, and every node in the cluster gets a subnet out of the default pool. That's the behavior, that's the state of the cluster after initialization. Let's create a new pool. The cluster is running in dual IP stack mode, so the pool is configured with both v4 and v6. What we have defined here can be translated to this YAML definition. So Cilium pod IP pool definition, name, IPv4 CIDR, mask size, IPv6 CIDR, and mask. And that's exactly what we also have defined here in a more human-friendly way. When I hit the submit button, the Kubernetes API request is sent to the cluster, requesting the creation of this pool. And on below, we have the logs collected dynamically from both Cilium operator as well as Cilium agents running on Kubernetes cluster nodes and filtering only the IPAM related logs. So since I have just created the pool and there is no deployment yet, no client of this pool, the only activity in the logs is on the operator level, which indicates that the pool has been defined. We also see here noted with the dashes, empty spaces, that this pool is not pretty much used. That's how you should interpret this output. The pool is defined, but it's not used. No node is at this stage requesting, or no node has allocation from this pool. So let's create some workload. I will create, for example, a pod. A single pod and node will be selected automatically by Kubernetes scheduler. If we wanted to see how it looks like from the lower level perspective, we have the pod definition. The pod is annotated with IP pool that has been defined in the previous step. The pod has a name, namespace, and the containers definition. So the only important or different configuration from the standard pod definition is this annotation. So when I hit the submit button, now a few things will happen. The pod was scheduled to run on kindworker 2 node by Kubernetes scheduler. That node did not have any subnet from the requested pool 66. So it was communicating with Cilium agent was communicated with operator back and forth. /28 has been allocated from the pool, and the pod on this node is allocated with the IP address from the pool. 1066.66.1 belongs to the pool allocated for that node. So let's create a second pod, but this time on a different node. So I will say specifically I want it to be deployed on a different node, but still I want to have only one replica. I specifically requested the second pod to be created on kindworker 3 node, which means that this node also requested another subnet from the same pool. That right now we have two pools, two subnets allocated from pool 66. One is owned by kind worker 2 node, another one is owned by kind worker 3. To double check, we see that the IP address of the second pod that I have created belongs 66.17.17 belongs to a different to the different pool allocated for kind worker 3 node. As a next test scenario, let's create pods on kind worker 3 just to see what triggers the allocation of another subnet on the same node. So how we do that? Let's still create the pods. Let's select kind worker 3, but we had it was /28. It's /28 is 16 IP addresses, but the first and the last IP address from this pool, as per implementation, as per documentation, it will not be used. So effectively, /28 subnet is good enough for 14 pods. I have one created, so let's create 14. If I create 14, I would expect that at least one will fall into the a second subnet. So let's do that. When all the pods are created, we see the outcome. We have in total 15 pods scheduled to be running on kind worker 3. But the subnet, which has been allocated on the node initially after the second pod was created, was only good for 14 pods. So there is one extra pod which goes into another pool, another /28 allocated from the same pool on the same node. That's how it works. If I would right now delete all the pods, then we should expect to see that the allocation usage of these pools per node goes down to 0, obviously, because there is no client, no pod deployed on that node for that pool, and these pools should be reclaimed by an operator and could be reused whenever needed. So let's see if that happens. When all pods are successfully deleted, the pools are released. We see that also here in the logs. And then there is no pool requested, allocated on the node, and all subnets are actually are back to the pool, and the pool can be used again whenever needed. Essentially, also the pool could be also deleted. As the last demo use case, let's create a very small, the smallest possible pool, which will be /32. And let's also keep the mask, obviously, also 32. It cannot be smaller, right? It's a single IP address in the pool. And similarly to the previous demonstrations, upon creation, nothing happens besides the fact that it's created. So let's create this time a deployment in that pool. I don't care which node it will be deployed on, as long as it's only one replica, one pod. Kube scheduler selected kind worker 2 node. That node requested a /32 subnet out of the /32 pool, so it could only get that single /32 subnet at the end. And the only allocation possible from that subnet is that IP address, which can be confirmed by checking the IP address of the pod. So we have a very precisely defined IP address for a pod. But the main reason for this demonstration is slightly different. What if I want to evict that node, that pod, to a different node? So let me do that. First, I will go to the nodes and I will mark kind worker 2 as scheduling enabled. So, sorry, disabled. So right now, kind worker 2 is marked as scheduling disabled. Let me, and if I check the pods on these nodes, on this node, one of them is this XXS pod backed by the deployment with 66 IP address. So let me hit this button to trigger an eviction of that pod. Right now, the Kubernetes eviction API has been called. If I go back to pod IP pools, we will see what's the final outcome of this eviction. The pod was evicted from kind worker 2 node. It was that another available node was selected by kubescheduler. It is kind worker 3. But in this very specific use case, since the pool that was defined was /32 out of the 32 subnet, the pod IP effectively keeps the same IP address on a different node. If you had a bigger pool from which you would lease /32 subnets, then very likely the pod IP address will change. But here in this scenario, the pod IP address behaves like a sticky IP. It's exactly the same regardless of the node location.